Okay, we're online. So hello everyone, and welcome to our 49th webinar of this series of these Latin American webinars of physics. My name is Nicolás Bernal, and I'm from the Universidad Antonio Nariño in Bogotá, Colombia, and I will be your host today. So the speaker today is Sebastian Ingenhütt from Technical University of Munich, and where he's a PhD student working in the group of Professor Alejandro Ibarra. So Sebastian will talk today about dark matter and the decaying dark matter to the gravity portal. And we're super glad to have him here today as our speaker. So first, let me remind you guys that you can be part of the discussion, writing your questions and comments via the YouTube live chat system. Okay. And now I can hand you over to Sebastian. So are you there?
All right, thank you. Thank you very much for the kind introduction and for having me, for allowing me to present my work in this format. Yeah, so like you already said, yeah, the topic today is going to be gamma rays from light dark matter decaying through a gravity portal. So just for a bit of context, I guess this is the third in a series of 3 papers that I've been working on together with Oscar Catar and Alejandro Ibarra here in Munich. So the last one, this one appeared July this year. And so in the context of these papers, we're talking about dark matter that decays through a nominal coupling to gravity. And so I will refer to the previous 2 papers that you can see on the opening slide throughout the talk, but of course I will try to make it self-contained. And for the purpose of this talk, the focus will lie on light dark matter in the MeV-GeV mass region. We will see how this sort of framework leads to gamma ray signals, which might even be observable depending on the coupling size, of course. Right. So this here is my outline for today. I will start out with a brief motivation. So it's going to be about global symmetries that stabilize dark matter against decay and the interplay between gravity and these global symmetries. Then I will explain the setup in a bit more detail. So dark matter that can then decay via this sort of operator that we dubbed gravity portal interactions. And then we will look at the experimental signatures that we studied. So in this case, the gamma ray flux I would expect from this kind of coupling and limits we can get from the CMB. And then finally, I will conclude and show how far we can already constrain this nominal coupling. So since I have 30 minutes, I'll have a dark matter introductory slide. So since the 1930s, of course, we have had an increasing a number of observations that show us that give us evidence that there is a dark component in the cosmological fluid, that we have some dark matter component, and we have evidence on multiple distance scales at this point. So if you look at galaxies, where the rotation curves that we measure require the galaxy to be embedded in a dark matter halo for it to be consistent with Newtonian predictions, or whether you look at the collision of galaxy clusters here, you look at the gravitational lensing and you see that the mass distribution is not centered on the distribution of visible matter. Or if you look at the CMB, the temperature fluctuations, and you compare that to a prediction in the lambda CDM framework, you can see, of course, this perfect agreement here if you include a dark matter component into the equation. So we have evidence at multiple scales now, but all this evidence is, of course, based on the gravitational interactions of dark matter. So, of course, over the past decades, we've tried to measure dark matter properties in other ways. We've got direct detection experiments, we have indirect detection, and we try to see if dark matter has other interactions. But well, the simplest dark matter candidate, I would argue, is that of a particle that is uncharged, collisionless, and stable, and might just interact gravitationally. So you might have to think about, well, what if dark matter really only interacts gravitationally? Can we still hope to see it in experiments and to find out about its nature? But then, of course, we can relax any of these three assumptions here. So we can, for example, look at milli-charged dark matter, or dark matter that's charged under a dark gauge group or something. We can look at dark matter with self interactions, which might help with what people call small-scale problems with lambda CDM. We can also look at dark matter that's not absolutely stable, but that can decay and potentially give us signals that way. And this is what I'm going to talk about in this talk here. So let's focus on the third part here, the stability of dark matter. So what we know from observations is that if dark matter is made up of particles, they need to be extremely long-lived. So the dark matter lifetime needs to exceed the age of the universe, which is about 10 to the 17 seconds. And this is actually quite long. So if you think about the visible sector, only very few particles have that kind of lifetime. And it's usually linked to a stabilizing symmetry. So the electron, for example, is stable because it's the lightest charged particle. The lightest neutrino is stable because it's the lightest fermion, and so on. And likewise, the stability of the dark matter particle could be due to some symmetry protecting it. So this might be a dark age symmetry, or it could just be like a global Z2 symmetry. So, for example, in the scalar inner doublet model, you just have a second Higgs doublet, which is stabilized by a global symmetry that you introduce to the model. Alternatively, of course, dark matter doesn't have to be absolutely stable. The axion, for example, can decay into photons, but because of its tiny mass, the decay rate is so low that it's still perfectly fine with observations. Right, so the next thing to maybe think about in this direction is then, if we have a global symmetry that stabilizes the dark matter candidate, then what happens if you add gravity to the equation? So there are arguments in the literature where gravity does not conserve global symmetries. So I'm not going to pretend I'm an expert on these kind of papers, but for the purpose of this talk, let's try to just be agnostic and just say, well, what if the dark matter particle is stabilized by a global symmetry that is broken by gravity? So this is the kind of framework that I want to talk about, and this is the framework, as I said, that we first talked about in these previous two papers that you can already find in the archive. So the scenario is that of a dark matter candidate where its non-gravitational interactions preserve global symmetry, like global Z2, so it's stable against decay. But through non-minimal gravitational interactions, the Z2 is broken and the dark matter can decay through this gravity portal. And in this case, the long lifetime of the dark matter particle is linked to the Planck suppression of gravitational interactions. So that's one nice feature. Right, so in order to break like a Z2 symmetry, stabilizing the Z2, we need to non-minimally couple the dark matter candidate to gravity. And this can be seen quite easily. So if you start like with a general Lagrangian like this here, and you couple it, the dark matter field phi minimally to gravity, of course, afterwards it's still going to be stable. So we need a Z2 breaking operator. So from an EFT standpoint, we asked ourselves, well, what is the lowest dimensional non-minimal operator coupling dark matter candidate to gravity that conserves Lorentz and standard model symmetries but breaks the C2? And the answer is surprisingly simple. So in the three scenarios that we talked about and that I'm going to mention later in the talk, it always has this form here where Xi is a dimensionless coupling, R is the Ricci scalar, and then F1 of phi is a function linear in phi with mass dimension 2. Now, of course, you could couple, you don't have to couple to the Ricci scalar, you could couple it to the Ricci tensor in some covariant fashion, but we found that in the three scenarios that we studied in detail, the lowest dimensional operators always turn out to be proportional to the Ricci scalar, actually. Right. So if you add this kind of operator to the theory, what happens is that you mix the dark matter candidate and the graviton. And then what that means is that because gravity acts universally on the visible sector in the sense of the equivalence principle, this means that the dark matter candidate ends up with a universal coupling to the visible sector, and it can decay into visible sector particles via intermediate gravitons. So this can be seen quite easily. So this is a bit of a math-heavy slide here. But so if you take the metric tensor, you expand it around a Minkowski background, and here lambda is the graviton field and kappa is the inverse reduced Planck mass, then expanding the Ricci scalar around this background means you have terms with two derivatives here, and then terms linear or quadratic or higher order in the graviton field. So then if you have a non-minimal coupling term like this, where m here is a mass scale and phi is just the dark matter candidate, then of course if you multiply this by the Ricci scalar, you end up with these kinetic mixing terms here. So then what you want to do is to bring the kinetic Lagrangian into canonical form. You want to diagonalize it, and you do that by performing a Weyl transformation of the metric tensor. So you take the metric tensor, multiply it by this function omega squared, which is essentially 1 plus this non-minimal coupling structure here. And then afterwards in the Einstein frame, you end up with canonical Einstein gravity for the gravitational part and a modified matter Lagrangian here, which is now expressed in terms of the Einstein frame metric and picks up a prefactor omega to the -4. And so in the Einstein frame, the gravitational sector is canonical. You just have pure Einstein gravity, but the matter Lagrangian is modified, and because this function omega includes the dark matter field, you end up with explicit couplings between the dark matter candidate and the visible sector. So schematically, what happens is in the original formulation, in the Jordan frame, you have a kinetic mixing between phi and the graviton lambda, which then couples to the visible sector, whereas after diagonalizing the kinetic terms, the dark and the gravitational sectors are decoupled, and the interactions with the visible sector are manifest in this form. Right, so as I said in the previous two papers, we already talked about heavier dark matter above the GeV scale. So in this case, the visible sector is just given by the standard model degrees of freedom. And then we looked at three scenarios. So we looked at a scalar singlet, a scalar doublet, and a fermionic singlet. And in each case, we tried to find out what is the lowest dimensional non-minimal operator of the form that we want. So for the scalar singlet, it's really simple. You just have the coupling here, the Ricci scalar, a mass scale, and the dark matter field. For a scalar doublet, this mass scale m here is replaced by the Higgs doublet. So H1 would be the standard model Higgs, and H2 would include the dark matter candidate as its neutral component. And then for the fermionic singlet, you need to make the operator Lorentz and gauge invariant. So the lowest dimensional operator here is actually at dimension 6 already, where L is SU2 lepton doublet, and H1 against the standard model Higgs, and chi in this case is the dark matter candidate. And so for these three scenarios, what we did in these previous two papers was to compute all the partial decay rates, the branching fractions. So on the left-hand plot here, you can see the branching ratios as a function of mass between a GeV and 10 to the 8 GeV. So as you can see, since the coupling to the visible sector is universal, the branching ratios depend on the dark matter mass. So, for example, at the GeV scale, you mostly decay into Ws or Higgs bosons. At lower masses, at the fermion thresholds, these channels spike up. So, because the coupling is universal, you preferably decay into final states that have a similar mass to the dark matter candidate until you reach this high mass region here, which is kind of cut off, when you decay into the states with the highest particle multiplicity. And then what we did was to compute the total lifetime of these dark matter candidates. So this is the total lifetime in seconds as a function of the dark matter mass between a GeV and 10 to the 12 GeV. And the orange dotted dashed line here is the age of the universe, 10 to the 17 seconds. This 10 to the 24 seconds is the this is the kind of typical limit you get from neutrino telescopes for the lifetime of dark matter decaying into final states with neutrinos. And as long as the dark matter lifetime, which is plotted here in red, blue, and green, is above these, then everything's fine. But as you can see, at very high dark matter masses here, the lifetime drops below these values for order 1 couplings for xi equal to 1. So then we would need suppressed coupling, suppressed non-minimal coupling for the scalar doublet and the fermion singlet. But for the scalar singlet, in fact, the total lifetime always lies below this the age of the universe for order 1 couplings. As a summary of the first 2 papers, if you want, so since the scalar SU2 doublet and the fermion are additionally protected against decay by gauge or Lorentz symmetry, we can allow order 1 couplings up to masses of 10 to the 5, 10 to the 6 GeV. But for the scalar singlet, because it doesn't have this protection, experiments might be sensitive to order 1 couplings. So, I mean, this is the coupling that always appears in the rate. So xi is the dimensionless number, m is the mass scale, and kappa is the inverse Planck mass. So for order 1 couplings, we might be sensitive even at sub-GeV dark matter masses. So this means maybe we have a signal in the gamma ray flux, and maybe we have an imprint on the CMB. So for the purpose of this talk, I will talk about scalar singlet dark matter now in the light mass region, so kind of below the GeV scale, so to the left of this point here. So yeah, explicitly below 700 MeV. Right, so in this case, the classical action takes this form here. So we have the Einstein-Hilbert term in front, kappa again is the inverse reduced Planck mass, R is the Ricci scalar, then you have this non-minimal coupling structure here, which is exactly the same as the one I showed you before. And then we have an effective Lagrangian for the observable sector and a dark matter Lagrangian, of course. And now in the observable sector, below the GeV scale, this effective Lagrangian describes photons, neutrinos, the light leptons, and pions. Whereas the electric gauge bosons and heavy fermions are integrated out. And then the dark matter Lagrangian, we don't specify any closer. What we do assume is, as I said before, that in the absence of gravitational interactions, Z2 is conserved. So dark matter is stable as far as its non-gravitational interactions are conserved, and the only are concerned, and the only Z2 breaking term is the non-minimal coupling to gravity here. And then as before, we can decouple the gravitational and the dark sectors via this Weyl transformation here. And then we end up with a canonical gravitational action, the Einstein frame, but we modify the matter Lagrangian at the same time. So explicitly in the Einstein frame, the observable sector effective Lagrangian takes this form here. So TF, pi, and gamma are the kinetic terms for the fermions, pions, and photons. And V is the potential with all the mass terms. And all these different terms pick up prefactors with omega. And the exponent depends on the Lorentz structure of each individual term. So the potential doesn't have any contractions with the metric tensor. So this is why it picks up an omega to the 4. The kinetic term of a scalar has 1 metric tensor in it. So this is why it's an omega to the 2, and so on. Then for small field values and small couplings, so if this combination here is smaller than 1, we can expand these prefactors in powers of the non-minimal coupling. And then, of course, the linear terms, the terms linear and phi, will explicitly give us the decay vertices. So on this slide, you can explicitly see 3 of the vertices that you can just read off in the Einstein frame formulation. So all the vertices are proportional to the non-minimal coupling, proportional to xi times m. All the couplings are, of course, also Planck mass suppressed. They all have a kappa squared in here. And what you can also see is that there's basically 2 kinds of couplings. So the two-body decays usually are proportional. So the vertices are proportional to the masses of the final state particles. And then there's another kind of vertex which comes from the gauge interactions, which is proportional to the gauge couplings. And then in the mass region that we're looking at below a GeV, the decay modes that we find are into photons, neutrinos, light leptons, and pions, as I said. One other subtlety that arises in this framework is that when transforming into the Einstein frame, when transforming the Ricci scalar, there's an additional term in the dimension that appears. It looks like this, so it's the derivative of this omega factor here squared. And what this does, because omega includes the dark matter candidate, what this does is it modifies the kinetic term of the dark matter candidate. So you need to redefine the scalar field in the Einstein frame to bring the kinetic term into canonical form. And this essentially introduces this prefactor here, square root of 1 plus 6 times non-minimal coupling. And this has quite subtle consequences, actually. So this means that all the vertices are also divided by this factor here. So all the decay rates are proportional to this expression here on the bottom of the slide. So this means that for small couplings, xi m kappa, the rates go as the coupling squared, whereas as soon as the coupling is larger than 1, the rates grow increasingly insensitive. So in the limit xi m kappa to infinity, this just goes to a constant. So the rates go, like I said, we lose sensitivity to the coupling. But I will comment on that later in the conclusions and how to make sense of that. Right, so what we did next was to compute all the partial decay rates again. So these are the branching fractions of a scalar singlet between like an MeV and a GeV roughly. So below the electron mass, we have photons and neutrinos to decay into, but the decay into photons is the dominant one. And then, as I said, since the coupling is universal, you'll always decay into final state particles with a similar mass. So at the electron, muon, and pion thresholds, these two-body decays, they start dominating the rate very quickly. Whereas then here, somewhat later, the three-body decays take over. Right, so let's take a quick step back and look at what we have. So we saw how such a gravity portal coupling, such a non-minimal coupling to gravity, leads to universal coupling to the observable sector. And we have specifically in the MeV to GeV scale mass region, we have decays into gammas, leptons, and pions. So this means we might have spectral features in the gamma ray flux. So specifically, if you look at the channel phi to gamma gamma, for example, this would be the perfect channel, of course. This would give you a gamma ray line, which would be easily visible above the background. But in our framework, this channel is loop suppressed. The particle rate is very low. So for order 1 couplings, you wouldn't see it. The next channel here, the phi into two neutral pions, is also very nice because when these pions decay into pairs of photons, they give you a gamma ray box in the spectrum, which is distinguishable above the background. And this channel has a much larger partial rate, so this could be visible for order 1 couplings. And then finally, there's an additional bump-like feature from these three-particle vertices. So from these channels, we expect spectral features, which should in principle be detectable over a smooth background. So now we can confront these with the measured X-ray or gamma ray flux. So in order to do that, we computed the gamma ray flux that we would expect from dark matter decay. And the gamma ray flux here at Earth is made up of these two components here, which turn out to be roughly comparable in size. So we have the cosmological dark matter. So this here in front is the dark matter number density, the average number density. And you integrate over redshift, you sum over all the final states. And these are the photon spectra evaluated at redshifted energies. And then you have a second component from our own Milky Way halo that we modeled with an NFW halo. And in this case, of course, the gamma ray flux you expect is depends on the direction you're looking at. So you have to integrate over the line of sight. And then what we did is to average over all the angles to get the average flux we expect that we then can compare to the isotropic flux that we see in experiments. And the channels we included for these calculations were the ones that produce hard photons, which are visible above a smooth background. So in this plot, you can see the gamma ray flux as a function of energy for dark matter candidates of different masses. So this is for 550 and 500 MeV for a non-minimal coupling equal to 1. And this is the gamma ray flux for these two contributions I just mentioned. And you can also see the data points are the X-ray flux measured by integral and the gamma ray flux measured by COMPTEL, EGRET and Fermi LAT. This is the isotropic diffuse gamma ray flux. And as you can see already above 5 MeV, the flux from dark matter alone that we would expect for order 1 couplings can be larger than the total measured flux by orders of magnitude. So even without making any assumptions on the astrophysical backgrounds, we can constrain the lifetime of the dark matter particles. So this is what you end up with if you do that. So this is the limit on the dark matter lifetime as a function of mass between a bit over an MeV to a GeV. So the limits lie in the ballpark of 10 to the 24 to 10 to the 27 seconds, as gamma ray limits usually do with current data. So this dip to the right here is at the muon threshold, because then you don't get any that many hard photons, and this is when the pi0 channel kicks in again. And then another way we can find constraints on this scenario is looking at the CMB. So for this, we followed an approach suggested by Tracy Slatner and Qilian Wu in a paper that they uploaded to the archive late last year. And I'm just going to briefly explain how it works. If you're interested in details, you can ask me after the talk or look at their paper directly. So essentially, the impact that a generic dark matter model has on the CMB mostly depends on the energy that you inject in the early universe into the intergalactic medium. And the main impact of a generic dark matter model is due to the electrons and photons that you dump and that you use to ionize, heat, or excite gas. So then what you can do is to define a set of basis models. So for example, you fix the species, for example, electrons that you inject, you fix the injection energy, and then you can compute the effect of these basis models on the CMB. And this is what these people did, and they're providing interpolation tables online here for people to use. And then what you can do is you can derive a constraint on a generic dark matter model by just decomposing that dark matter model into a linear combination of these basis models, which essentially means you compute the electron and photon spectra, and then you convolve them with detectability functions for electrons or photons. And then an approximate limit on your generic dark matter model on the lifetime is given by a weighted sum over the limits on these basis models. Right, and that's what we did. And so on this plot here, you can see the limit on the dark matter lifetime as a function of mass from the CMB. So the plots for gamma gamma and E plus E minus were already published in the original paper. These are these ones we reproduced. And then the other colored lines are the other partial rates that appear in our scenario. So for example, the limit on pi0 per 0 is a bit stronger because you get 4 photons instead of 2, for example. And then the black dashed line is a combination of these limits taking into account the branching ratios of our dark matter candidate into the individual channels. And the channels we considered for these limits are the same ones as for the gamma ray limits, plus cascade decays into pions, where the pions decay into muons, and then the muons decay into electrons, and so forth. So all channels that produce photons or electrons that way. Right, and then finally you can convert all these limits on the lifetime on constraints on the non-minimal coupling parameter. And this is what you can see on this plot. So this is the limit on this combination xi and kappa as a function of mass between an MeV and a GeV. So the shaded regions are excluded. So the green, blue, and red regions are regions that we exclude based on the gamma ray data. So these are calculated by demanding that the gamma ray flux from dark matter decay does not exceed the total measured flux of these experiments by more than 2 sigma in any individual energy bin. And then the black shaded region is the limit from the approximate limit from the CMB that I just described. So the CMB limit is slightly weaker over most of the parameter space, which means we can still improve the limits with upcoming experiments such as Amigo or eAstrogam. You can see the muon and pion threshold nicely here. And what you can also see here to the left is that the limits turn upwards sharply at order 1 coupling. So this is exactly what I talked about earlier. So because the rates are proportional to this factor here, as psi m kappa goes to 1, or grows larger than 1, the rates grow insensitive to this coupling. So if we can't constrain the coupling to be smaller than 1, we can't constrain it at all. Right, this already brings me to my conclusion. So we saw that based on the evidence that we have, we require dark matter particles to be extremely long-lived. So this might be a sign that the dark matter candidate is stabilized against decay by a global symmetry. So then I try to motivate to you our idea of looking at what happens if gravity breaks such a global symmetry, like a global Z2. And in this case, the gravitational effects are actually the dominant ones, because the non-gravitational interactions of the dark matter candidate we assume to conserve this Z2. So we can hope to see these gravitational interactions. And then we saw how such a gravity portal scenario, such a non-minimal coupling to the Ricci curvature, leads to a universal coupling to the visible sector. So the preferred final states depend on the dark matter mass. And then we saw how specifically a dark matter candidate in the MeV to GeV mass range produces photons, electrons, muons, and pions. So for order 1 couplings, we would expect a spectral feature and the gamma ray flux, so we would expect an imprint on the CMB. And since we don't see any of those already with present data, we can constrain this non-minimal coupling to values smaller than 10 to the minus 2 for a scalar singlet above 15 MeV in line with the CMB limits. Now, one thing that one, of course, needs to think about is, well, is that a small value? Like, what is a natural value of this kind of non-minimal coupling? And of course, well, this might look similar to our models of Higgs inflation, where you have a similar operator that couples the Ricci scalar trilinearly to the square of the scalar field. And in order to be consistent with inflationary observables, you need this coupling to be like 10 to the 4, 10 to the 5. But of course, this is a different operator than our operator. So this is it looks similar, but it's a different scenario. So you shouldn't compare really these two numbers. And yeah, what's also interesting is this sensitivity cutoff at large coupling that I talked about, due to the field renormalization, because the rates, as I said, are proportional to this factor here. And one way to make sense of this is if you think about how we define the non-minimal coupling, kind of somewhat redundantly split up the coupling into a into a dimensionless number xi and a mass scale m, whereas the coupling only really appears in this combination. So what we could have done instead was to just introduce a mass dimension 1 coupling mu, which would be xi times m, and then this this expression here approaching 1 would mean this coupling approaches the Planck scale. So then couplings larger than 1 would correspond to mass scales larger than the Planck scale. So this is why this might not be so transparent what happens there exactly. But this is mostly an issue for the scalar singlets. For the scalar doublet, for example, you would also get a correction like this, but here the mass scale is the electroweak scale. So this means you have like V over m Planck down here. So unless this non-minimal coupling is of order like 10 to the 16, you wouldn't see this this modification. Anyways, I guess it's a good time to stop at this point. Thank you for your attention, and I'll be happy to answer any questions you might have.
Okay, great. Okay, thank you, Sebastian, for this super nice talk. So before starting with the question, let me remind you guys that you can ask questions to Sebastian via our chat in the YouTube website. So are there questions from the audience, from the local audience here?
Yes. Can I ask something?
Sure, go ahead, Diego.
Hi, to initial question, how do you avoid the Higgs portal? relate. Oh, okay. The other question later, maybe.
So we don't actually. So I mean, we avoid the Higgs portal by demanding or assuming that the non-gravitational interactions of this dark matter candidate are Z2 conserving. So we assume that in the if you take gravitational interactions out of the picture, then the action is conserves Z2, so you don't have any linear terms. So if you're talking about the Higgs portal with a dimension 1 coupling, this one is forbidden by the Z2 symmetry. Now, of course, you can have dimension 4 Higgs portal, like phi squared h squared, and this term is very much allowed. That can be in the potential, but the point is that that one doesn't induce dark matter decay because it's quadratic in the dark matter field. It can, of course, give you a scattering or something.
But this kind of term, phi squared, h squared, can induce another signal.
That is true. That is true. You can have signals from annihilation from that. That is very much true. Yeah. We just wanted to look at what the effects are of this non-minimal operator that give us decay. So, but of course you would see additional features. But this, of course, depends on the coupling parameter then to the Higgs portal, to the Higgs doublet. Yeah.
And my second question is if this dark matter candidate can also be used as the inflaton.
That's a good question. Yeah, we actually looked into that. So there are papers in the literature already actually that that try to do something like this. So they introduce non-minimal coupling to gravity, and then they try to make the to both include to make it the field both the inflaton and the dark matter candidate. But so in these papers, at least in all that I've seen, they were looking at again at this Higgs portal kind of interaction, which is quadratic in the dark matter field. So in our case, it doesn't really. So it doesn't work with the linear coupling itself, because what you need for Higgs inflation to work is for this potential to go to a constant value, right? And this is based on the fact that the potential has a quartic term, and then you have this non-minimal coupling squared in the denominator, which gives you an h to the 4. So in the large field limit, it goes to a constant. But our operator is only linear in the dark matter field, so it would go as phi squared. So if we have quadratic terms in the quartic terms in the potential, we didn't have a plateau at large field values. So what we thought about was to look at the scalar doublet scenario. So in this case, of course, you have two scalar fields, and then you could think about regions in parameter space where you can find inflation there. But then, of course, you in addition to this this operator that I showed in my talk, then of course you need to also consider the two non-minimal couplings to the Ricci scalar that are quadratic in the individual fields. So you would have Xi1 are h1 squared plus Xi2 are h2 squared plus Xi3 are, and then the product of the two. And then you would need to, I mean, then what you could do is just to use one of the operators for the decay, the one that couples h1 to h2, and you could have inflation with one of the diagonal operators. This is actually what people have looked at in literature. But just from this operator that we introduced alone, it's hard to do.
Okay, thanks. Are there more questions?
Yes, I have another question.
Sure, go ahead, Juan.
Yes, my question is regarding the choice of the specific form of the non-minimal coupling term, which is linear. Usually, you see that this coupling term is quadratic. I mean, it's C times the Ricci scalar times the field to the power 2. over a mass term. Why you use this linear term? And an advantage of this quadratic is that there is a connection with this conformal coupling limit for the scalar field, which is kind of important. So and the other advantage is that you only have one parameter, which is this psi, which is this dimensionless, and instead of two, you have this m parameter, this mass parameter at this psi. So I was wondering why you use this linear coupling.
Well, that's true. I mean, we need the linear coupling such that dark matter can decay. If you look at these operators that are quadratic in the dark matter field, of course you can induce annihilation into visible sector particles, but we were interested in decay, so the operator has to be linear in the dark matter field.
Okay. Okay. Have you also considered kinetic couplings? Are there other possibilities to introduce nonlinear coupling? And a very famous one is to introduce kinetic coupling to gravity.
Right.
And in these cases, I think that it is also possible to introduce decay.
I mean, like I said, the form of these operators. So all the operators I was talking about were proportional to the Ricci scalar. But like I said, of course, you don't have to do that. You can couple it to the Ricci tensor. So you can have something like R mu nu and then d mu phi, d nu phi, sometimes something like that, like coupling with a derivative coupling. But these are higher dimensional operators. So we found that the lowest dimensional ones were always proportional to the Ricci scalar. So this is why we focused on those. But you're right that in principle you can of course write way more of these operators, which are then higher dimension. Right.
Oh, okay, thank you.
Can I comment on that, or maybe just continue with the question? So your choice, this operator was really a choice, right? So these are by mass, scale, and the field. It's not that you naturally produce such a term.
No, I mean, we introduced this operator by hand. So, I mean, for example, the quadratic operator that we were talking about earlier, I mean, this one, for example, arises in curved spacetime just even if you set it to zero from the beginning just by loop diagrams. So this doesn't happen for this operator that we were looking at, of course. So you're right in the sense that we introduced this operator kind of ad hoc. So the justification, as I said, is that, well, we don't know what quantum gravity ends up doing. We just made the assumption that somehow it breaks this global Z2 symmetry. But then from an EFT standpoint, well, what is the lowest dimensional operator that we can write down that has these properties? And then these are the operators that we found. Right, this is...
Yeah, thanks. Sure. Are there more questions?
I have a question. Herman. Okay, thank you. It's a very short question. It's about, well, I was late. I don't know if you mentioned this. Well, there is this new proposed telescopes to look for MEV gamma rays. Have you take a look to those prospects that you, I don't know if you can improve with those kind of new telescopes? Also, I think there is this Chinese telescope that is already taking data that they claim that can go very low in the gamma ray signal.
Mm-hmm. Yeah, so the two I know of are E-astrogam and Amigo, which are both, however, still in the process of being suggested and approved, or maybe not, and you know. So of course we would our limits will get stronger with this additional data because the CMB limits are weaker than the gamma ray limits. This means that the CMB doesn't preclude this kind of coupling, so we could improve our couplings with additional data. Yeah, I haven't looked at the specific prospects though, so I can't tell you any numbers.
Well, the point is that if the community start to say that, well, we need that kind of telescopes, making prospects of using those telescopes, maybe they will approve.
Right, right.
We will give more.
So maybe we should look at how much it gains us. Yeah.
Yeah. Then maybe this is some kind of support for the people doing that proposals.
Yeah.
Thank you.
Okay, so I have a question for Sebastian. So it's regarding the question that was before the one of Herman. So with this minimal coupling or with gravity, in principle, you're going to break not only the Z2 symmetry in principle. I mean, you're constructed to break the Z2 symmetry, but in principle, the same mechanism could apply for any global symmetry that is present even in the standard model. For instance, lepton number could be broken in the same way, no?
Right.
So, and then the other question regarding with the same problem, I mean, not problem, with the same idea is that at the end, when you break, when a global symmetry is broken in this type of models, then as soon as it's broken, the radiative correction is going to start to mess up all your parameters of the model. How you kind of control this type of effect, like chain reaction that has to break this. The stability of the matter is going to start to affect other type of processes, in some sense.
I'm not sure if I understand your question 100%. So you're right in that if we assume that gravity breaks this global symmetry, of course, we should also expect it to break other global symmetries. Yeah, definitely. We've only looked at what happens to dark matter stability, though. So we haven't looked at what happens to other global symmetries in this case. Yeah. So maybe that's the answer to the question. We don't know. We haven't checked.
No. It's just not a question, but maybe it would be also interested to relate it with the for neutrino masses or something like that.
Yeah.
No, but I was more trying to understand the part of radiative correction, because this is usually a problem that happens with other models, that as soon as you break the symmetry, the global symmetry that is protecting some observable, for example, the radiative correction is going to start to move all your parameters to such value that it seems tend to be order 1. This type of parameter grows very fast. I mean, even though they are very small, they grow fast. So, and in that case also is because what you were talking in the talk is remind me this conjecture that if quantum gravity is present and has effect in particle physics, observables, no global symmetries should be permitted. I mean, gravity would break any global symmetries, and one way to escape that is to promote your global symmetries to gauge symmetries. Is it possible to have the same approach with this type of non-minimal coupling, to instead to have a Z2, to have a U1 gauge in your dark sector and try to non-minimal couple to gravity in the same way without like surpassing this type of conjecture?
Yeah, I mean, the thing is, if your dark matter candidate is stabilized not by a global but by a gauge symmetry, for example, well, then you would expect it to be stable also as far as its gravitational interactions are concerned, right? So, I mean, what we did see was that, so for example, the scalar doublet, because it has its charge under SU2, so it has some sort of additional protection against decay. So the limits were much weaker than for the scalar singlet. But yeah, just on very generic grounds, I mean, this argument only holds for global symmetries. So if the dark matter candidate is charged under a gauge symmetry, then we would expect it to be stable.
Yeah, so that means that this type of non-minimal coupling are forbidden by default, let's say.
Yeah.
And another question I was also wondering, because you apply this idea to scalar dark matter. Is it possible to realize it in the case of Fermi dark matter?
Yes.
A la gravitino light in that sense, even though it has to have, could be a spin 1/2 only.
So this is we actually looked at that fermionic dark matter in the previous paper. So the one before, we had a longer paper where we looked at scalar singlet dark matter, scalar doublet dark matter, and then a fermion too. And so the general phenomenology is similar. So you end up with a universal coupling to the visible sector and so on. But the difference is that the lowest dimensional operator that you can write down for a fermion is of higher dimension than for the scalar singlet. So maybe I can show my slides again with the non-minimal operators for the fermionic case. Let's see. So the operator that we found for the fermion had this form here exactly. So we need a lepton doublet to make it Lorentz invariant, and then a Higgs doublet to make gauge invariant. So the operator's dimension 6. Now this mass scale here, of course, well, you could either say, well, this arises some sort of quantum gravity effect, so you could set this to the Planck scale, but this kind of operator can also appear, for example, if you start with a scalar that couples non-minimally to gravity, like this, like if you have two scalar fields, and then this scalar couples to the dark matter candidate chi with the Yukawa kind of interaction, then you, if you integrate out the heavy scalar, you end up with exactly an operator like this, where m is the mass scale of the heavy scalar. But yeah, of course, it also works for other spins.
Oh yeah. So the term is going to be similar to the Gravitino one, more or less. At least the output signal, the observable, is going to be a neutrino with a heavy Higgs. I mean, with a Higgs or with a Z boson, depending on the case. So yeah. So yeah, no, that was the question that I have. So thank you.
Okay, I have a question. So at the very beginning, you say that your lowest non-minimal operator is proportional to the Ricci scalar, but not to the Ricci tensor. Is that obvious?
Well, if you take the Ricci tensor, for example, if you want to couple it to a scalar, then where do you get the Lorentz indices from? Then you need derivatives of the scalar field.
Okay, yes.
So yeah, and then for the other. So for the fermion, it's slightly more. So for the fermion, we had a couple of candidates, I think, but they all ended up either being identical to 0 or higher order. In all three cases, it's not quite as obvious as for the scalar, but for the scalar, it's like that, more or less.
Okay. Are there more questions from here? Okay, I see that in your chat you have at least 2 questions. One is from Maria Ángeles Pérez Garcia. So she first said, great talk, Sebastian. And then she's asking, do you think that other finite-sized stellar objects, I think she's thinking about neutron star or something like this, where gravitational redshift is strong, could lead to some signatures?
Well, I mean, I'm not sure how exactly the question is meant. So, of course, these gamma rays that we get from this kind of interactions are just like regular gamma rays from dark matter decay. So maybe the question is related to since our operator is based on gravitational interactions, if there was some sort of change close to regions of spacetime with high curvature, like close to heavy objects, and this question I would answer with no, because in the Einstein frame, the gravitational action is absolutely canonical. You just have Einstein gravity, so and you just have a dark matter candidate which has direct couplings to the visible sector, which with a universal coupling. So this is, I mean, the peculiar feature of this kind of operator. So we don't expect any exotic effects based on the value of space-time curvature just from this kind of operator. Yeah, so I'm not sure if that answered the question 100%. So of course the gamma rays from dark matter decay via this interaction would undergo gravitational redshift. as photons do.
Okay. And there's another question from Nicolas Fernandez. So he first say that thanks for the great talk. And then he's wondering about the dark matter relic abundance. So he asked, what's the production mechanism for this dark matter? Do you produce the correct dark matter relic abundance?
That's a very good question, actually. So, I mean, for the purpose of this paper and also the two previous papers, we haven't actually looked at producing this kind of dark matter. So what of course doesn't work is a typical freeze-out scenario, because all the interactions are Planck mass suppressed, so the couplings are all very, very low. So you do get, I mean, if you take these prefactors omega and you expand them like we did, you do not only get decay vertices, you also get like scattering vertices. So you could try to produce dark matter that way, but it would have to be some sort of freeze-in scenario with a very, very low coupling. And this is actually something we want to look at in the future. Alternatively, the production of this dark matter candidate does not have to be linked to this non-minimal coupling to gravity. So, for example, for the scalar singlet, we could just imagine we have a Higgs portal coupling in the potential, like h squared phi square. We produce the dark matter via the coupling to the Higgs, just a regular freeze-out. But then looking at the decay phenomenology, that is governed by the non-minimal coupling to gravity. So yeah, this is the standpoint that we took in this paper in particular. We didn't make any definitive statements about how we produce it, but it's definitely something we want to look at if we can produce it with the same kind of operator. Yeah, thank you for the question.
I guess that the freezing will always work, no? Here.
Yeah.
Maybe.
Should.
Okay, are there more questions?
I have one very basic question connected to the last question. So if you don't know how much dark matter you have, how strong does that make the bound due to the lifetime? Right, because of course the lifetime doesn't mean that the dark matter will decay all at once, right? So how much space do you have left, to play with the lifetime bound?
Well, I mean, we know how much dark matter there is just from observations, right? From Planck, we know.
No. I mean the one that you start with.
I'm not sure I understand the question.
So you will start.
Okay. I think I got it now. So I mean, in all these, I mean, we demanded the lifetime of the dark matter candidate to always be longer than the age of the universe. So we assume that the abundance does not change significantly over the cosmic history. Yeah, that is true. Right. Yeah. So is that the answer to your question? So we assume the dark matter to have a lifetime much longer than the age of the universe, right, such that the abundance remains essentially constant.
Right. But if you allowed that to change, then the bound on the lifetime wouldn't be such a hard bound, right?
Yeah, but I mean, as we saw, the bounds you get from cosmic ray experiments, so from the gamma ray flux, or from neutrino telescopes, are stronger than the requirement that the lifetime be longer than the age of the universe. So this means we would see signals in these experiments long before the lifetime of the dark matter candidate drops below the age of the universe.
Okay, perfect. That answered my question.
Okay.
Thank you very much.
Okay, great. Maybe a last question?
Yes, for my part, it is possible to have dark matter masses around 100 GeV in the singlet case.
100 GeV. So yes, definitely. So I mean, this is actually part of the analysis that we did in one of our previous papers. So let me just bring up this plot here again. So I mean, it all depends on the coupling. So for xi equal to 1, at say 100 GeV, a scalar singlet would decay far too quickly. So in this case, you would need the non-minimal coupling to be suppressed by many orders of magnitude to push this limit up above the age of the universe and then above the detection limit of cosmic ray experiments. For the scalar doublet or the fermion singlet, here, as you can see, the lifetime is way above these two limits here, even for order 1 couplings. So in this case, it could the coupling could be order 1. Yeah, but it depends on the scenario and on the value of the non-minimal coupling, of course.
But wait, Sebastian, at some point you say that you want to restrain yourself to dark matter lighter than 700 MeV or something like this.
Yeah, this was for the last paper that I was talking about primarily in this case. So because in this case you have these gamma ray signals that I was talking about. So for large dark matter masses, you decay here into W6s, so you get different kinds of final state particles. So this is why, for this talk, I was focusing on light dark matter.
Okay, that was a choice, I see. Okay, I think that's all, no? No more questions? So, okay, so let me thank you, Sebastian, once again. So it was super nice to hear about this research. And one more thing, let me remind you that in 2 weeks we'll have, I forgot. Okay, we have a great talk. It will be a surprise. And so hope to see you in 2 weeks from now, guys. So thanks a lot, Sebastian, and see you all soon. Ciao.
Thanks a lot.